these are quite interesting and suggest how to apply their practices in how to apply what we have learned about finite groups. Okay. So have a look at least. Okay. It will definitely come useful at some point. So today I will continue with examples, okay, of Lie groups, okay, of groups, Lie groups in quantum physics. So last time we gave a lot of examples of matrix groups, okay, groups which come from looking at some quadratic form which is left invariant. But I told you that there are many examples in physics where this is not the case. Okay. So we want to look at them. Okay. I think I mentioned translations, okay, last time. I think so. Okay. There are groups like translations which are not in their origin as transformation groups. So okay, there are many cases where symmetry groups arise as not as linear transformations. In physics. The simplest example is n-dimensional translations. Okay. That I think you know what it is. We have seen Poincare group. This is not a group of linear transformations on a vector space in their origin because it involves translations. But equally important, we know something which is quite important in non-relativistic physics, Euclidean group. In 3 dimensions of translations and rotations. Okay. This is quite common, we deal with this all the time, but then we also deal with something related, the Galilei group. Say in 3 dimensions. This is the stuff of non-relativistic physics. Okay. So it consists of the Euclidean group. Okay. Let me call it Euclidean group. Plus velocity transformations. Like x going to x plus vt. Okay. These are the Euclidean velocity. So if you go to a moving frame, the position coordinates will change with time like this. Okay. So this is the Euclidean velocity transformations, not the Lorentzian transformations. Okay. Actually, this group, by the time you go into quantum mechanics, exhibits some very strange feature, okay, which some of you may want to look up. Okay. In quantum theory, this group gets changed you get something. This isn't. It is not this group. You get something slightly different. Okay, it gives mass superselection rule. Let me mention this. What is a superselection rule? You are taught in elementary quantum mechanics that if you have any two state vectors, you can superpose them, right? That's what you are told in ordinary quantum physics. Vectors can be superposed. But what happens when you have superselection rule is that there is no observable, okay, superselection. Means there does not exist something you can see observable k such that chi k psi is not 0. Okay, that means if that happens, you can never observe the relative phase between psi and chi. Nothing. So the superposition is a futile activity. So it becomes regarding this. I mean, this superposition principle has no meaning, okay, because there is no cross term which will ever appear in physics. Okay. So what happens in non-relativistic physics? This is a result due to, as usual, I think. This famous paper, Wick-Whiteman. There is a WQ paper, Wick-Whiteman Bigdan. Who first discussed this phenomenon, and they were the ones to point out that the Galilei group, the way Galilei group changes when you go into quantum theory, which was known for some time, actually leads to this peculiar thing that in non-relativistic physics, you cannot superpose vectors with different masses. Okay? So if you have a free particle of mass m and a mass m prime, you cannot. If you have Galilei invariance, there is no meaning in superposing. Okay? So similar things in quantum field theory, one cannot, or it is useless to superpose states of different electric charge, wave functions of different electric charge, for example. Okay? So this is something to notice. Okay. So, but I want to discuss that in physics, we get groups, we get quite routinely infinite dimensional groups. Okay. Which are not canonical, which are not of, well, let's say, which are not well understood, let's write. The most striking thing is the following, striking example, group of canonical transformations. In classical mechanics. Okay. What are these? Okay. These are acting on phase space. Okay. You know what is a canonical transformation? Have you come across it? You have come. Okay. Huh? I will write it down. Okay. These are, if you have a definition is the following. Okay. They act on a phase space okay. So normally we have, these are phase spaces some with coordinates. Well, so with Poisson bracket, I should really write simplex Poisson. Let's write some. Fg, say F1, F2 at Qp is equal to, normally we write epsilon Rs d F1, if I call this as psi, d psi r d F2 over d psi s, okay, where this epsilon Rs, okay, is antisymmetric. So, it is of the form epsilon is 0, 1, minus 1, 0. Okay. This is antisymmetric form. The Poisson bracket can be written like this. These are evaluated at the point psi. Okay. So, you get dq, ddq, ddp minus the other term. This is antisymmetric. Now, the canonical transformations are basically diffeomorphisms of the phase space, leaving the symplectic form, this epsilon invariant. Okay. So, a canonical transformation is huge. Okay. Is a smooth map okay, psi going to phi of psi. So, if you like, the psi I goes to phi I of psi such that, okay, this form epsilon Rs, let me put, yeah, let me put psi I here, d phi r of psi d psi I d phi s of psi d psi j is epsilon ij. Yeah. So, yeah.
This is just the same as saying if I have two functions and I compose them with this phi.
This invariant, yeah. It preserves the Poisson brackets. Okay. So, it is so this involves functions. If phi's are linear in psi, okay, phi's are linear in psi, okay, we get the SP groups. Then these differentials become constants, okay, and you get the standard stability groups. Okay. But here they involve functions. Okay. They are actually what they call it symplectomorphisms or something. Okay. They are diffeomorphisms leaving the symplectic form invariant. So, and they involve functions. Okay. So, these things involve, so these involve functions. Whole functions is huge. Okay. And if you, I mean, if you want to deal with them, you have to tell what kind of functions you are dealing with. It gets very complicated. But in one dimension, let us say one spatial dimension. Okay. If you are doing phase space of a circle, okay, then there is a considerable control on this group, okay, and it is known variously as Virasoro group and so on, okay, and it comes in conformal field theories. When you consider phase transitions, they play a dominant role, okay. So that is under control, but the moment you go into higher dimensions, one does not know, okay, and invariably you do not know how to use them in quantum physics, okay, except in the rarest of cases. Okay. So these are too big. Too big, I should say too big. Classical mechanically they are quite very much used for solving differential equations. That is quite common. Okay? But those techniques won't work in generally in quantum physics. Okay? The unitary representations of these groups, okay, are not known. Okay? I mean, yeah, they are not known. I mean, you cannot even write the operators properly in quantum physics. I mean, what is angular, what is the general infinitesimal operators for these groups? One does not know how to write them, okay, because there are operator ordering problems. Okay, how do you put the position and momentum operators? What order gets messed up? Okay. Okay. Now there is another group. Okay, there are more things. Okay. In successive levels of complications, okay, you have in gravity. Okay, one gets involved with the full diffeomorphism group. Of space time. You know what I mean by diffeomorphism group? It's just mappings like this on a manifold, okay, which takes a point of the manifold to another point, okay, but in a differentiable way, infinitely differentiable way. This comes in any kind of gravity theory. Okay, this is in fact the defining property of a gravity theory, and how to handle it in an appropriate way, okay, I would say is not very well understood. Okay, not understood. Okay, there are some crude results which are known, okay, which I hope to explain a little bit in the Monday morning lectures. Okay, so there are when you try to understand them, quite difficult, quite precise technical problems arise, okay, which are not very well understood, but they are essential, for example, to define, for example, what is angular momentum of a black hole, okay, because angular momentum is related to rotations, and rotation is a diffeomorphism, because it is just, so you have to know how to handle that. Okay, it is even worse. It could be that let me give you an example. Could be the following: you have a plane. Suppose your space is a plane, okay, and in the middle you do the following. You put a torus. How do I write it? Yeah. You attach a torus on the manifold. Okay, so it's a pimple on a plane. Okay, far away it is flat, but inside there is a torus. Okay? So far away, the question is there can it define an angular momentum associated to what is happening here? So can I rotate infinity, rotate far away? Can I make a rotation there in such a way that this rotation is defined everywhere? Can I? So I make a rotation like this. Yeah? Then I go on, but when I hit this, what do I do? Okay. What is the rule? How do I extend this transformation to the interior? Okay. Can you do it? Most of you would say no. So the rotation is not defined. But that's not true. Okay. If that were the case, then angular momentum and mass and so on in general relativity cannot be defined. Okay. Because you don't know what is happening in the neighborhood of a black hole and so on. You have no idea. Okay. So can you define this? The answer is yes. But how do you do it? Very interesting. They are not geometrical. They are I don't know what language to use. Very interesting problems arise. There are very interesting solutions of this issue, okay, which are known to people who do low dimensional topology. Okay, and it was taught to me by Raphael, okay, Sorkin. Okay, they are very beautiful. Okay, but one has to address many such issues before you can have a handle on this diffeomorphism group. Okay. But I should also say, since some of you will go into quantum field theory, gauge group. So this is another example. Then another classic example is gauge group. These are also these are also bad stories, because here what you do is, given a Lie group like, okay, U1 just one time, or SU2 whatever, a gauge group, it is not this that is a gauge group. The gauge group, so call this Lie group like G. Okay. The gauge group I should probably call it script G associated G. Okay. Or I can write like this, the gauge group, let me call it MG, is the space of smooth maps from space-time M to G. If you don't understand this, you can ask. So what it does is following. So if I take a point P in M, I'll give you an example, then, and G is in this gauge group, then G of P is in G. Okay. So it is mapping a point of the space time into a Lie group. And what is the multiplication? G1 G2 with G1 G2 at P, because the target is a group, you can simply write this as G1 P G2 P. Right? So the gauge group is not a group G, SU2. QCD or so if you do electromagnetism, QED or QED, the group is G, let's say your Minkowski spacetime M4 into U1. U1 is electric charge, this is the first. So here what happens is, you take point X, okay, G of X is of the form exponential I lambda x, okay, this is U1. So this is real, right? An element of U1 is a phase, so I can write like this. Well, lambda is a real number, lambda x is a real number. So the image of this, so G I am writing as exponential I lambda, but it involves this function. Okay. Of course, we assume appropriate smoothness conditions. It is an enormous group. I mean, it is as poorly understood as any of the other examples. Okay. Again, in the rarest of rare cases, one has a good control on what it is doing. Yeah. So there are all these things, and to some extent we understand, but there is a lot. I mean, if you treat, very often the handling of this group is done a posteriori. There will be some physical motivation on what exactly you should do. Okay, then you put conditions on this functions lambda that come. Okay, and how to and their handling in quantum theory. Okay, so yeah.
Diffeomorphisms are characteristic of theories of gravitation.
Yeah.
So, is there any natural choice of constraint that restricts the size of the group? Like, there's nothing, because so, like you said, for the group of canonical transformations, when you consider linear canonical transformations.
That one,
is there something like
that people do normally, what they call what they call mini superspace models and so on. No? If you reduce the gravity theory to something simpler, which people often do, they are called generically by this phrase mini superspace models, okay, where you throw away all degrees of freedom except very few, 2 or 3, and reduce it to some very simple model. Okay. There you know, if in that model what are the stuff which should act, okay. That is understood, okay. That because it is so simple you can handle it. For example, mini superspace, for a black holes for example, you can just take into account the symmetries of the black hole, which is rotations and translations, okay, something like that. Then you can make models with those, okay. Or the loop gravity, people do it quite often. Our friend Alok gave a talk the other day, okay, and also I think people here are doing such things. Okay. So in those cases you can reduce the problem to a much simpler case, but whether they are realistic one does not know. Yeah, I mean there are also all kinds of problems which should not be covered here, but there are all kinds of problems like these are associated to Gauss law. All these diffuse are associated to all these kind of thing, gauge transformations, and correspondingly gravity are associated to Gauss law. So what is a Gauss law? Gauss law is 0, right? Divergence of E is 0 or J 0. Gauss law says something is 0, right? Is 0, right? It is what that's the equation of motion from electromagnetism, right? In quantum theory this becomes an operator equation, but this is the one which generates a diffuse in some way. But then you can ask if all the diffuse act trivially on the quantum state, or this is the one which generates gauge transformations in quantum theory. So if everything is gauge invariance means this vanishes on the states. Then where is the electric charge? Okay, how do I define electric charge is supposed to be associated to this, no? Where did it come from? Because if everything goes away, okay? So where is everything should be neutral, but that is something wrong, okay? So what is wrong? So technical problems arise in treating operators in quantum field theory, even in the simplest of physical cases, okay? Even this, okay? So now I want to make a remark. Note, this is just a curiosity. GL and C, okay, can be realized as a subgroup. This is something strange again of SL n plus 1C. I just give this remark. It is an occasional use, okay, by the map. I told you, no, A going to SLN, no? So it will be A determinant of A inverse. Okay. One dimension higher, but since determinant doesn't vanish, so this is overall determinant 1. And I also showed you how this thing can be UN. So UNC, UN is a subgroup of, I told you, what does it go? SO2N. You remember this? You can realize UN, this is actually quite important, and I did it in passing, provoked by some comment by her. Okay.
Is that you blow up each?
I remember I replaced, basically I was replaced by this 2 by 2 thing, right? we route this as real part plus I times imaginary part every element, then I we blew up into 2 by 2, okay. Then yeah, because this is real, but epsilon squared is, epsilon has all the right properties, okay. Square is -1 and everything, and it realizes takes this and puts it there, okay. This is quite a useful thing, okay, and it comes in discussions of if you look in Ed Witter's this Green-Schwarz-Witten on string theory, there is a whole section on Kähler manifolds, okay. What is a Kähler manifold, and you will find this isomorphism used extensively, okay. Now what I am going to do now is to go into the, so what I will do is the following, okay. I will first start about the issues of paths, okay, and connectivity of Lie groups of G. What do I mean by it? Okay. Then I will do invariant integration this is very powerful, okay. Will lead to, okay, this will let us, okay, lift results from finite to, I will define what I mean by this, compact groups. I will define compact in a more trivial way. You will find that every one of the results that we have here you can put there, okay. Yeah. Character, everything you just copy, okay. Except that integer, the dimension of the finite group is replaced by something called the volume of the continuous group, that is all, okay. And thirdly, okay, how Lie groups, I will first show you how, I will not give proofs, lead to Lie algebras. I will not give you proofs, but I will give you plausibility arguments. Proofs are quite elaborate, so it is not necessary to be able to handle what is happening. Then the Lie algebras go to Lie group G, Lie algebras take you back to G, not exactly G, it is a covering group of G. So this is big to small, back to big. That is, the Lie group is a complex variables. If you know analytic functions of a complex variable, if you give me the analytic function of a complex variable, I can restrict it to some small neighborhood, right, and look at the Taylor series. And if you give me the Taylor series around any point, I know the complex variable function completely by analytic continuation, okay. It is a similar process that is happening, because there is the whole thing is tied together in a very strict way, okay. The only thing here is that when you go to the large, from here to here, you do not generally recover the group. For example, from the Lie algebra is infinitesimal object, something with some structure, okay. For example, if you take the case of angular momentum SU2 or SO3, SO3 is rotations. If you go here and go backwards, you do not get back SO3, you get SU2, the twofold cover, okay. So, and there is a technical reason for it, okay, which we shall also try to appreciate. Okay. Whenever there are nice arguments, I will give it. When the arguments are too long, I will not. So that is a general principle, okay. So now I want to define, okay, paths, okay, in G. So Lie is a Lie group I will say that this is simply a smooth map from the real line to G. So I have a mapping T going to G of T, and it is a smooth curve. So where G is a matrix group, this is topological groups. So example, suppose G is say SU2, SUN. Okay. So these are matrices G. Okay. A path is T to G of T, Gij of T is smooth in T. So the continuity is simply taken as element by element continuity. This is the old when you have matrix groups, what is meant by nearby matrices is what exactly you expect. Okay? They are all coming from the matrix elements being close to each other. No further trial or no further activity is required. Okay? So why did I start? Okay, I should say that two elements G1 and G2 in G are connected sometimes they say pathwise connected. Okay? If there exists G of T in G such that say G of 0 is G1, there is a path G of 1 is G2. Okay. So I can connect them by drawing a line. So I have G1 here, G2 here, and I can draw a curve. Okay. For example, if you consider O3 and I have, suppose R and S are in O3 and determinant of R is +1, determinant of S is -1, then since that determinant is a continuous, so it's a determinant of any element RST, T of T is continuous in T, continuous in the small variable. Okay, we can say that RS are not connected. Okay, they are disjoint sets. Okay, so you cannot draw a curve. Whereas SO3, I might also say here, but SO3 is connected. Why? Because that lets me introduce what SO3 looks like. Okay? Because by Euler's theorem, by Euler, every rotation is a rotation by an angle theta right, around an axis n, right. This is what Euler tells you. So every rotation r, so every rotation can be written as some, let me write like this, exponential theta n dot j. Never mind what, j is your angular momentum operator if you want, okay. You can write like this, or n dot sigma O2 or whatever it is. Okay? But the main point is the following, but rotation by pi, okay, around n and minus n are same. Yeah, because 2 pi rotation being 1. Is identity. So how will I write SO3? So I can write SO3 out. So this is a SO3. It's a ball, 3-dimensional ball, right? A point here, so this is an origin, a point here, so represent SO3 by, this is a notation, by ball B3, okay, a point in P in ball, okay, gives axis n, which is this vector OP, okay, and angle theta is equal to length of OP. Okay, this length of this line, I should say 3 of radius pi. Okay, so the radius of this ball is pi. But because of the thing I told you, antipodal points on the surface are identified. Okay. Identify antipodal points on surface. Okay. So this geometrical picture, so I will identify this point and this point, identified. Okay. So this is a picture of your R rotation group. Clearly it is connected, because clearly I can draw curves between any 2 points. So this manifold, you know what this manifold is? SO3 as a manifold, what is this called? You know it? It's a RP3. It's a projective RP3. Okay? It's a projective 3-dimensional manifold. So you take lines in 4 dimensions, 4 real dimensions. So you take lines in, imagine, let me say, if you take project RP2, what is RP2? If you take RP2, you are taking lines, this is a space of lines in through the origin in 3 dimensions. So RP2, what you will do is you will take a point and take all lines. They are lines, one dimensional subspaces, real subspaces like this. So R is a projective, take all one dimensional subspaces in 2 one dimensional subspaces RP2. P2 is 1 dimensional, 2 dimensional, forget. Yeah, so 1 dimensional subspaces in 3 dimensions, 3 dimensions, take in lines. Okay. So what do? I can, to find representatives of each line, I put a sphere around it. It will cut the lines, but it will cut each line 2 points. So you have to take S2 and identify opposite points. Okay. So that gives you RP2. Okay. This is this cross cap. This is not an orientable manifold in 2 dimensions. Okay. Similar thing in 3 dimensions is called RP3. Okay. So you take lines in 4 dimensions. Okay. So you take lines and imagine cutting it by a sphere, but each sphere will cut the same line twice. So you identify them, you get this. So it is connected. Okay.
Of course, that sphere is SU2.
The sphere is SU2. Okay, that I will come to later. Okay, it's a twofold covering. We will come to that. In fact, you know that the sphere is SU2. I have shown it many times. Okay. So why am I doing all this? In this process of discussing Lie groups, we have to discuss the connected component G0 to identity of a Lie group. Okay.
So the way you have defined RP3, so isn't that like S3 quotient Z2?
Z2.
But here, aren't the points in the interior also in the manifold?
They are in the manifold.
So it's
But no, it's not like that. It's not like that. For example, if you take RP2, how will I represent it? Suppose I want to represent RP2 with opposite points. You will take the sphere, right? But opposite points are identified. So you will cut it. So it will look like a disk. Because this part is the same as that. I'll just, right? I'm identifying this with this. So cut it. Forget about it. You get this. But here opposite points are identified. Right?
I think he's right. I mean, you can think of it in 2 ways. Like RP2, you could think of it as 3 sphere. Sorry, 2 sphere, where you make just the skin, where you make the antipodal. Or you could first take the sphere and collapse the 2 hemispheres to get the disk. So that's a solid disk. And then you could identify antipodal down. So in analogy, if you want to get RP3, you could deal with the 3 sphere, which is just skin, and do the identification. Or somehow collapse that to get the ball, solid ball. So then the interior would be, and then you would do the antipodal identification of the 3 spheres.
Are you following? Because it's the same thing and it's the same thing. Okay. Okay. So I want to discuss this. Okay. What is the idea? The state claim is the following: there exists a neighborhood, okay, U of identity of G. Okay. So say let's say G of epsilon belongs to U and this epsilons are all very small. All these epsilons are small, okay, say less than some epsilon 0. It's a ball, okay. You choose some parameterization. The point is that it's a small neighborhood such that, okay, if g of epsilon belongs to U, the inverse belongs to U. This is the point you were raising the other day. Okay. In U, okay, the G and the inverse belong to U. Okay. You can prove this existence of this neighborhood, but from what I have seen in books like Pothriagan, it requires solution of differential equations. So I won't do it here. Okay. In practice, you will see what it is. The main point is that this element is inverse belong to U, okay, and it is connected. Okay, notice that G is connected. Okay. Note U is connected. Okay, since, okay, every G epsilon, I should say here also, is connected to identity which I choose to be G of 0. So I should say G of 0 is identity, that is a choice of coordinates. Okay.
This statement is for a compact group.
No, for every Lie group.
No, but what happens if you take the multiplicative group of positive reals and you take
One, there is a neighborhood to the identity. 1 is identity.
Yeah, but if I take something smaller than 1, let's say something like 0.8, and then I take its inverse, I take, right?
This simply existence of a small open set. For all Lie groups, this is true. Okay. The U is not unique, okay, but there exists one U. U is called the group germ. By Weil. Okay. The point about this U is, the whole point is I am trying to shrink the big group to a small region, because I'll show you, okay, from U we can recover G0. In fact, okay, okay, G0 simply the union over K of U to the K. Okay, U to the K is U. Okay. In the non-compact case, here there are problems. Okay. You have to do some funny business of limits, but for compact groups you see by explicit examples this is the case. Okay. So by taking U and all its powers, by U squared I mean you go on taking all possible cross terms. Okay. You fill up, you take the small thing and blows up and fills the whole group. Okay. So why? At least I can show, okay, that this union K, U to the K is a group. Let me at least show you that. this is rather easy because for all k, okay, for if okay, G is in u to the k, okay, and H is in u to the m, then I can write G as G1 up to Gk, okay, Ga is in u, H I can write as H1 up to Hk, Hm, Hi is in u, okay, and you can see that implying Gh is belonging to u to the m plus k, k plus m. Similarly, G inverse, okay, also since Gi inverse is in u, G inverse, which is Gk inverse, G1 inverse is in u to the k. So for sure this generates a group, okay. The technical points are that you can cover the whole group, which is straightforward in the compact case by some activity with covering compact spaces, which is in Pontryagin. In infinite case it is not, the result is true, but I don't know how to prove. I think Pontryagin proves it, but I don't know, okay. But main point is that Pontryagin proves, shows, okay, that this group does not depend on choice or u. I mean, group germ is not unique, okay. So you have to be vary, okay, whether you get different answers by choosing different u, okay, but that is not the case. The main point is this group is what is called the connected component of G. This group, the union of this G0, this group, okay, this union G0 by definition is this connected component, this union of u to the k, and is connected. Main point here is that it is connected. Okay. So I will show that to you tomorrow, okay, by noticing that this object here, this u I am writing, this u is connected to identity, right? It is like a, what is this? This kind of thing is called star shaped. That is, if you take the origin epsilon equal to 0, you get whole line in a small neighborhood in this set, right? The whole line is going, if I replace epsilon by t epsilon and make t go to 0, I get a whole line. It is always inside, okay? So it's star shaped, it looks like a star. So it is easy to show that u is connected, okay. Did I say it here? I just made it here, made the statement. I will repeat it tomorrow, okay, and just show a small proof. Using that fact, you can show that this G, the group I am getting here is connected to the connected, okay. So it's a connected group which is living in the whole Lie group, but it may not be in fact it will not be the whole Lie group in general, okay. This part of the whole Lie group we can handle by infinitesimal methods, because all its properties or almost all its properties are encoded in this group germ, okay. So from the main point about the group germ is that its properties are completely determined by the tangent space at the origin of this germ. It is a small area, you can actually go to the tangent at the origin, okay. the properties of this tangent will enable you to recover this u. Okay, what are the properties of this tangent that gives you the Lie algebra? So we are successively reducing a whole big group into a small, in fact the tangent space of the origin, okay, and from there recovering the whole group. So we will do that step by step tomorrow. Start by proving this, then I will keep going. Okay, but in between I will stop this development and show you how to do invariant integration, because that before I go to Lie algebras, that is very useful because it automatically gives you a lot of things, but it requires this concept. Okay, because the way I integrate depends on the existence of this d0. Okay, so I will stop here.